Today we are going to derive the formula for a trapezoid. Now a trapezoid, as you can see, is a quadrilateral. Now we know it's a quadrilateral because it is a four-sided closed shape. And what you're seeing underneath here is just another trapezoid. It's a complete double of the other one. We're going to use him a little later on. I'm going to put him over to the side. And now the reason why we cannot just use a simple formula for a trapezoid is because the area formula is a little different. So we know for normal quadrilaterals, we're just going to use length times width. But if we look down at our trapezoid, we can see that it doesn't have a length times width. What it has is a base sub 1, a base sub 2, and a height. So what we need to do is alter our trapezoid so that we can work with it as some type of quadrilateral that we're a little more familiar with. So the first thing we're going to do is we're just going to cut this quadrilateral in half. So the height, I'll go ahead and tell you, is 12 units, and we'll just count that just so everybody knows. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And in order to cut that in half, we need to cut to 6. 1, 2, 3, 4, 5, 6. And I want you to notice that we are cutting across horizontally at the height, not vertically. So we're going to snip that right quick. Whoop. Okay. So as you can see, I've colored this so that as we move around and rearrange, we're going to be able to clearly see our original bases. Base sub 2 is blue, and base sub 1 is purple. All right, and our original height is pink. And now our original height has actually been halved, so we have two pieces of our original height, but the bases have stayed intact. So what we're going to do now is use the moving and additivity principle to kind of move this around to see if we can't get it into some sort of shape that we recognize. Just going to move this around some, try different things. That's not going to work. We don't know what shape that is. Nope. 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 And so when you cut shapes up like this, you can just keep playing with it. Eventually you're going to find a configuration that works. But what configuration I see is a parallelogram. And we do know the formula for a parallelogram. And I'm going to write that down for you guys right quick. You should remember, but I'll write it anyhow. You write it here more towards the top. Area equals base times height. And so here on our parallelogram, we can very clearly see a base and a height. And so what I'm going to do is I'm going to label our brand new base and height for this parallelogram. Our height is right here. It's this dotted line. And that's going to be our height. Our base, now that I've got it stuck back together the way it's supposed to be, is just going to be this long line either at the top or at the bottom. We know that those are congruent, but we're going to choose to do the one at the top just so we don't interfere with our old lines. I'm just going to turn these a little bit so that I can color them very clearly for you all. And just to elaborate right quickly on why we know that those two bases are going to be congruent, it's just one of the properties of a parallelogram. And it's a property of squares as well as rectangles. If we're going to be able to take this base, it has to be the same as this base in order for this whole area formula to work out. All right, so now we've got our new base labeled. We're going to just put a nice capital B here. Let me flip that for you guys. Sorry, I am not the best upside down writer. So now that's right side up for you all. So great, we just turned a trapezoid into a parallelogram. But that does not really help us with what we were doing originally, which is our original goal was to derive the formula of a trapezoid, not to be able to find the area of a parallelogram. So what I want you to do is just return back to our paper down here. And so I want to talk a little bit about what our new base, the green capital B, and our new height, the orange capital H, correspond to on our old trapezoid. And that's when our buddy will come back in over here, but not quite yet. Just keep him in your mind. This was our original trapezoid. And just to make sure you guys know they are definitely the same, I'm going to line these back up. Not like that. As you can see, they perfectly cover one another up. So it is the exact same shape. I've just left it whole. So let's put our parallelogram back together now. If I can. There we go. All right, and flip it back around so you guys can read it. So our height, if you remember, this orange capital H corresponds directly to half of our old height. And the reason why I say half is because if we put our old guy up right here next to him and we count the units, this is 1, 2, 3, 4, 5, 6 units tall. And our original trapezoid was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 units tall. So I'm going to write that down over here. Our height, capital H, of the parallelogram. Let me flip this upside down because, like I said, if I write upside down, nobody will be able to read it, is simply 1/2 of our original pink height. All right, there's that back for you guys to see. So now we know what this H equals for in the trapezoid. We want to know what this B equals, this green capital B. So we talked earlier about how this base and this base are congruent. They're exactly the same. The only reason I chose to color this base green instead of this base was because this base is already colored with the blue and the purple. So remember I told you guys at the beginning that I was going to leave this intact. This is base sub 1 in purple. This is base sub 2 in blue. And as we can see, those bases have remained totally intact. I'm just going to line those up for you guys. That's base sub 2 in blue. And this is base sub 1 in purple. Exactly the same. Nothing has changed about them. But what we can see from looking here is that this base sub 1 and base sub 2 need to be added together in order to make this whole base that we know for a parallelogram. So that's what we're going to write down here. And again, upside down writing is no good. So our capital B green base for our parallelogram is equal to our base sub 1 plus, write that with my black here, our base sub 2. And again, I'll flip that over so you guys can see that. All right, and we can still see this here pretty clearly if we bring it back up again. This is our green base that we're saying here is equal to our base sub 1 plus our base sub 2. And we can read that right there. And like I said, we know that's congruent because our formula wouldn't work if the two bases weren't congruent to one another. And our height is just 1/2 of our original height. And we lined those up and counted those earlier. And so now what we want to do is simply plug in our values. Use a little bit of substitution property to plug in what we found to be true for our capital B and our capital H. All right, so I'm just going to do that right quickly and then we will talk about it. All right, and as I write this formula out, just want you guys to be thinking about really the commutative property, because once I turn it back around, you're going to be able to see that it doesn't quite look like what I'm about to show you in the book in a little bit. So what we've got here, by plugging in our formulas, this is our capital B here, our capital H here. Let me just draw a line for you guys that's a little more clear. And this guy belongs here. is that the area for a trapezoid is base sub 1 plus base sub 2 times 1/2 the height. And now when we look in our math books in really just a few minutes, what we're going to see written in the book is not that formula. What we're going to see is area equals 1/2 base sub 1 plus base sub 2 times height. Now you may be tempted to say, Miss Lusk, that's not the same. That's not what we found. And the commutative property would be there to say, you know what, you're wrong. Because with the commutative property, we can just move this 1/2 around because this is all multiplication. It doesn't really matter what order we're going to multiply them in because they're all going to end up being the same thing according to the commutative property. All right, so today we have derived the formula of a trapezoid using the formula that we already knew for a parallelogram.